In this video, we'll be looking at the double angle, half angle, and reduction identities for the trigonometric functions. So recall that sine of alpha plus beta was equal to sine of alpha times cosine of beta plus cosine of alpha times sine of beta. So we can use this to derive the double angle. This means that sine of 2 theta would be sine of theta plus theta. Then by the sum identity, that's sine of theta cosine of theta plus cosine of theta sine of theta. But since the order of multiplication doesn't matter, these two are the exact same term, so this is 2 sine theta cosine theta. So this is the double angle for sine. Also recall that cosine of alpha plus beta was cosine of alpha times cosine of beta minus sine of alpha times sine of beta. So this means that cosine of 2 theta would be cosine of theta plus theta, which is cosine theta cosine theta minus sine theta, which is cosine squared minus sine squared. Now, if we actually use this, we can derive two additional double angle identities for cosine. What we do is we apply the Pythagorean identity, cosine squared plus sine equals 1. Then, what we'll get, cosine of 2 theta, which is cosine squared minus sine squared. Replace cosine squared with 1 minus sine squared, which is derived from up here. So that's 1 minus sine squared, which is 1 minus 2 sine squared. If instead we replace sine squared, we'll get this. Right, cosine squared minus 1 minus cosine squared becomes 2 cosine squared plus 1. So these are two alternative double angle identities for cosine. Finally, recall that the tangent of alpha plus beta was tangent of alpha plus tangent beta all over 1 minus tangent alpha times tangent beta. So tangent of 2 theta, which is tangent theta plus theta, is tangent of theta plus tangent theta all over 1 minus tan theta. And this is 2 tan theta all over 1 minus tan squared of theta. Those are the three double angle identities. One for sine, one for cosine, and one for tangent. We will now use some of these. So we'll go ahead and verify that 1 plus sine of 2 theta is equal to sine of theta plus cosine of theta all squared. So let's work this time on the right-hand side. Expanding this out, we'll have sine squared of theta plus 2 sine of theta cosine of theta plus cosine squared of theta. Now we can order this in any way we want. So we can write sine squared of theta plus cosine squared of theta in one grouping, and then still have that 2 sine of theta cosine of theta. Now this piece is just 1. So we now have 1 plus 2 sine theta cosine theta. And now we can use the sine double angle identity to write that as 1 plus sine of 2 theta. Now let's verify that tangent of 2 theta is equal to 1 over cotangent theta minus tangent of theta. So we'll start with the left-hand side, tangent of 2 theta, and use the tangent double angle to write this as 2 tangent of theta over 1 minus tangent squared of theta. We can now multiply by tangent theta over tangent theta. to obtain 2 tan theta over tan theta all over 1 minus tangent squared of theta all over tangent of theta. The numerator is just 2. Then for the denominator, we get cotan theta minus tan theta. Alright, I just checked my source notes, and this up here is actually a typo. That should have been 2 over cotangent of theta minus tangent of theta, not 1. And so, oops, that's a terrible looking box. And verification is complete. Right? So now we're going to look at the reduction identities. We'll begin by using cosine of 2 theta equals 1 minus 2 sine squared. This gives us 2 sine squared is equal to 1 minus cosine of 2 theta. And so sine squared of theta is 1 minus cosine 2 theta over 2. So this is the sine reduction identity. Now if we use cosine of 2 theta is equal to 2 cosine squared minus 1, we'll get 2 cosine squared is equal to 1 plus cosine of 2 theta, which means that cosine squared is 1 plus cosine 2 theta over 2. And that is our reduction identity for cosine. Combining these two identities, we can get the reduction identity for tangent. So recall that tangent is sine over cosine, so tangent squared would be sine squared over cosine squared. Now we use the two identities we just derived. 1 minus cosine of 2 theta over 2, all over 1 plus cosine of 2 theta over 2. Those 2's are going to wind up dropping out, and we're going to be left with 1 minus cosine of 2 theta over 1 plus cosine of 2 theta. So this would be the reduction identity for tangent. What we want to do now is go ahead and write cosine to the 4th x in terms of single powers of sine and cosine only. So start with cosine to the 4th x. We can write this as cosine squared of x squared. Now the reduction, 1 plus cosine of 2x all over 2, and that should be squared. A half squared is a quarter. Now expand out 1 plus cosine 2x squared. We'll get 1 plus 2 cosine of 2x plus cosine squared of 2x. If we distribute that quarter through, a quarter plus a half cosine 2x plus a quarter cosine squared of 2x. Now we have to deal with that cosine squared again. And again, we'll use the reduction identity. Right? This will then become 1 plus cosine of 4x all over 8, right? Because it's 2 times now this 4 in the denominator. If we now add an eighth plus a quarter, we get 3/8 plus the cosine of 2x over 2, and then plus the cosine of 4x all over 8. That is what we wanted, and so we're done. Now we wish to verify this identity. Sine cubed of 2x is equal to 1/2 sine of 2x all times 1 minus cosine of 4x. So let's start with the sine cubed of 2x. This can be written as sine of 2x times sine squared of 2x. Now we're using the reduction identity on sine squared. 1 minus cosine of 2x. Of 4x all over 2. Now just rewrite this to make it look like the identity we want to verify. We have a 1/2, we have the sine of 2x, and then the 1 minus cosine of 4x. And finally, we look at the half angle identities. Using the reduction formula for sine, we'll get that the sine squared of alpha over 2 is equal to 1 minus cosine of alpha all over 2. This means that sine of alpha over 2 is plus or minus the square root of 1 minus cosine of alpha all over 2. The sine, whether it's plus or minus right here, is totally dependent on the quadrant that alpha over 2 is located in. Likewise, now if we use the reduction identity for cosine, then cosine squared of alpha over 2 would be 1 plus cosine of alpha all over 2, which means that cosine of alpha over 2 is plus or minus the square root of 1 plus cosine of alpha all over 2. And again, that plus or minus will depend on the quadrant that alpha over 2 is located in. And finally, if we look at tangent, we'll have tangent squared of alpha over 2 is 1 minus cosine of alpha over 1 plus cosine of alpha, which means that the tangent of alpha over 2 is plus or minus the square root of 1 minus cosine alpha all over 1 plus cosine alpha. And again, that sign will be dependent on the quadrant that alpha over 2 is located in. We now wish to evaluate cosine of pi over 12 and sine of pi over 12. Cosine of pi over 12. This can be written as cosine of pi over 6 over 2. And so the identity would tell us this is the square root of 1 plus cosine of pi over 6 all over 2. Now pi over 12 is located in the first quadrant, which means that cosine is positive, so we're going to keep this as a positive. This will give us the square root of 1 plus cosine of root pi 6 is root 3 over 2 all over 2. If we go ahead and simplify this, square root 2 plus root 3 all over 4. And continue to simplify. We get the square root of 2 plus root 3 all over 2. So this is for cosine of pi over 12. Now the sine of pi over 12 is going to be done in a very similar fashion. So we'll get the square root. Now it's 1 minus cosine of pi over 6. Again, pi over 12 is quadrant 1, sine's positive. This will give us the square root of 1 minus root 3 over 2 all over 2, which will give us the square root of 2 minus root 3 all over 4. And so we get the square root of 2 minus root 3 all over 2. And so that would be sine of pi over 12. And that brings this video to an end. In the next video, we will be looking at the final two identities, the summed product identities and the product to sum identities.